In this lesson, we're going to look at how the normal distribution can help us when we're dealing with a binomial model with a very large n size. And we'll discuss why we need to go to the normal model. So let's look at a specific scenario. Genetics say that genes children receive from their parents are independent from one child to another. Each child of a particular set of parents has probability 0.25 of having type O blood. Suppose these parents have 5 children, and now we're given our random variable. Let X equal the number of children with type O blood. And we're to make a probability distribution of this random variable, which means we're listing all the possible outcomes of that random variable and the chance that it occurs. So I'm going to set up a chart, and I'm going to have each x sub I equaling 0, 1, 2, up through 5. And now I need to find the probability of each of these events. So I would say that this is a binomial model, so I can do Binomial Pdf for each of the different random variables. And how do I recognize that it's binomial? I am finding the number of x successes in a fixed number of 5 trials. And it does satisfy the BINS acronym. All right, so I'm going to quickly do Binomial Pdf for each of these values using n equals 5 and p equals 0.25, and I would have 0 for the first. Put that in my calculator, and I'm going to go to 4 decimal places. So please pause the video and calculate the different probabilities. So there are all 6 different scenarios. And I also just want to illustrate that, if we had taken Binomial CDF, remember that sums your cumulative frequencies. So if you wanted to know the probability of 3 or fewer children having type O blood, Binomial CDF would automatically sum the probability of 0, 1, 2, and 3 together, and you could test that just to make sure you're understanding. Also, remember that your probabilities here need to sum to 1. Now, if you would check it, there's a good chance it's slightly off because of rounding issues. It would probably be 0.999. Okay, so then we're told to make a histogram of this binomial distribution on the graphing calculator. I'm going to just show you what I mean by hand, and then I'll illustrate how to do this on the graphing calculator. And so we have 0, 1, 2, 3, 4, and 5 children having type O blood, and we would put our probabilities on the x-axis. So I'm going to say 1/10, 2/10, 3, and my highest is 0.3955, so 4/10, and then you're doing a bar for each of these, 0.2373. So there's a quick look at how to make it by hand. I should label my random variable down here as x is number of children with type O blood. So if I were to describe the shape, I definitely see, I would say a right skewed shape, and it's got a single peak. To make a graph of the binomial distribution on the graphing calculator, I'm going to enter my data into 2 lists. So in list 1, I'm going to enter my random variable. So it could be having 0 children, 1, 2, all the way through 5 children with O blood type. Now in list 2, this is where I'm going to have the probability of exactly 0 children, exactly 1 child, exactly 2 having O blood type. So the easy way of doing this is let list 2 be a binomial PDF. So to do that, I'm going to go, notice I was level with L2, so I let L2 equal binomial PDF. So I'm choosing A. And again, it was 5 trials. the probability is 0.25, and my x value, well, it's going to vary. I need to do it for 0, 1, 2, 3, all the way through 5. So I'm going to say let my x value be L1. Okay, and then I hit enter. And so here you can see here it says L2 is equal to that function. And I hit enter, and that matches the calculations I did by hand. So if I want to graph this now as a histogram, if I go to stat plot, turn it on, I'm going to make my type be the histogram. L1 and L2 is where my data is at. And I just selected the wrong one. I need it on. I want the histogram. L1. My frequency is L2. And then if I do zoom 9 for zoom stat, and if I hit trace, I know I'm not seeing my histogram really well. So let's see what's going on here. If I hit trace, there it's seeing my bin. My first bin is between 0 to 5, so that put all my data together, and I'm seeing my probability is almost 1 because it's doing the sum of everything. That's just rounding error there. So I need to adjust this by hitting window. I could certainly, this is a small one, I could do it by hand. So for my x min, 0 is good. I only need to go as high as 5. For my x max, I'm going to have it count by ones. Now my y min, I don't need to go very low, negative 0.1, probably only like 0.5. I don't have to go all the way up to 1, probability of 1. And my y scale, I'm going to count by 1/10 to make it easier on my eyes, and now I'm going to hit graph. Okay, that looks a lot better. So now if I hit trace, let's see what I'm looking at. So here's probability. So along the y-axis is the probabilities. Here are my random variables, having 0 children with type O blood is showing me probability of 0.237, arrow over, 2 children, 0.39, 3 children, I'm sorry, this is 2 children, not 3. This is 0, this is 1, this is 2. That's why it's saying it's less than 3. So I actually need to go a little higher here on my window. I just realized I need to go as high as 6. So I can see my last bar. There we go. So how would I describe this distribution? I'm going to say it's skewed right. Single peak, skewed right.
So we just saw a binomial distribution that was skewed to the right. But sometimes a binomial distribution will be roughly symmetric, sometimes it'll be skewed left, sometimes skewed right. So here are 3 different probability distributions where the p-value is 0.8 in all of them, but check out what happens as n, like your sample size, increases. So, you know, if this were children again, this would be having 10 children, 20 children, 50 children. So as your sample size increases, look what happens to the shape. You know, fairly symmetric roughly, but look, it's more symmetric. Look how beautifully symmetric this is. And not only that, but isn't it taking on the shape of a bell-shaped curve, which really is signaling to my brain, gosh, that's looking an awful lot like our normal distribution. And that's true. So as my sample size, as n increases, my shape looks more and more like the normal distribution. And that's a good thing, because sometimes the binomial distribution, calculating a binomial model, gets really, really tough because the number of combinations, if you have a really large n size, is going to be a massive amount of combinations, and your calculator will overflow, and I'll show you what I mean by that in just a second. So we can use a normal model if we have a large enough n size, okay? Well, how large is large enough? We have something in statistics known as the large counts condition. So to use a normal approximation in place of a binomial model, there must be at least 10 expected successes and 10 expected failures. Well, how do I calculate that? So our expected value would be n times p. So you're doing n times p if that's greater than or equal to 10, and as well as your failures, so n times 1 minus p is greater than or equal to 10. It's okay to proceed with the normal model. So let's look at an example. The communications monitoring company, Pastini, has reported that 91% of email messages are spam. Recently, you installed a spam filter. You observed that the past week it okayed only 151 of 1,422 emails you received, classifying the rest as junk. Should you worry that the filtering is too aggressive? So what we really need to figure out here to answer this is, so what's the probability that no more than 151 of the 1,422 messages or emails is a real message? All right, so we are going to first have to check our conditions here. So quickly go through my conditions. Binary. So I have a success is a real message, failure would be spam. Do I have independence? Well, the messages arrive independently in my inbox, but I'm also going to say that 1,422 is less than 10% of all emails since I'm going to be sampling without replacement. N, yep, I got a fixed number of 1,422 messages, and S is the probability of a success is the same for each message. So it's okay to proceed with a binomial model. So it's okay to use, so I state that with my N and my P, with the two parameters, which are on the AP formula sheet if you forget for your binomial model. So I'm saying it's okay to use, but it's going to be difficult to work with. Why is that? Why is it going to be really tough? Well, I'm going to be ending up doing combinations with really large numbers, like combination from 1422 choosing like 151. And if I do that, if you type that in your calculator, you're going to see it overflows your calculator because there are a ton of combinations that fit that scenario. So it becomes really tough to work with. So what do we do when the calculator overloads? Well, fortunately, our normal model comes to the rescue if we have a large enough n size. Or I should say, well, how large is large enough? That's where we go to our large counts condition. I check, do I have 10 expected successes and at least 10 expected failures? If I do, I can go to the normal model. So checking for a normal model, I'm showing my large counts condition. I expect n times p would be 1422 times 0.09. I'd expect 127.9 real messages, and that's greater than 10. And here are my number of failures, 1,249.02 spam messages. So since both are greater than or equal to 10, it's safe to use a normal model. All right, so if I'm going to use a normal model, I'm going to draw it and I'm going to find the parameters of my normal model. And how do I get that? Well, I'm going to need my mean and my standard deviation. So from my formula sheet, my mean is going to be for binomial n times p, which is, let's see, 127.98. And I need my standard deviation, which is going to be the square root of n times p times 1 minus p, which, if I plug in, is square root of 1422.09 and 0.91, which is about 2 decimal places, 10.79. So this over here, I'm going to label my normal model with my two parameters of mu equals 127.98, comma, sigma equals 10.79. And I want to know, what is the probability that there are no more than 151 messages? So let's see, 151 is going to be about right here. I'm going to shade in my probability that I'm looking for. And how do I do that? Well, if I'm not doing it by standardizing, I could find a z-score, or I can just go to normal CDF on my calculator, where my lower bound, I'm going to put in -999. My upper bound is 151. Got make sure I label this and don't just do complete calculator talk. 127.98 is mu, and sigma is 10.79. Hit enter. 0.9836. So my conclusion, among my 1422 emails, there is over a 98% chance that no more than 151 of them are real messages. So this is suggesting that the filter may be working properly, that it's not too aggressive.